Okay, back to lesson part 2 for the horizontal resistor motion. Yeah, yesterday we did a question, a non-development question, question 3. Pretty crazy. Let's have a look at today's question, question 5. Question 5 is a development question, so let's see how hard this question is. So the engines of a submarine of mass m deliver a maximum driving force of F newtons. The water resisted motion with a force proportional to the square of its speed. Okay, the square of the speed, that's very, very important, square of the speed. Now the question for the first part, you need to explain why dv over dt, which in this case dv over dt is just equal to a, is equal to that expression here. And then the summary increases the speed from v1 to v2, show the distance traveled during this period of time is equal to that expression here. So that should be a quite an easy question. Last lesson, for the first part 1, we did a similar questions where the speed is increased from a certain number to another number, and then we need to calculate the distance has been changed. Okay, right. So let's start with the question. First step here, we need to write down everything we have. Right, we have the driving force. The driving force is just equal to F. And then we also have the water resistance, okay, or the resistive force. So the resistance is equal to the square of the speed, okay, that's important. The square of its speed, okay, that is what the resistance force. So the square of the speed, all right, so in this case is v squared. But then just because it's proportional to, alright, so therefore we also need to have a k in the front for the proportionality constant, okay, so just a k, alright, just directly proportional to, so we don't really know, what is the constant number in front of the v squared, so we'll just put a k there. Alright, so once we finish this, alright, let's just draw a diagram like last lesson. Alright, so imagine this, this submarine is moving towards this right hand side with a driving force F newtons. There's a water resistance going this way here, and the water resistance is equal to kV squared. Now remember, the resultant force is still going from the left to right. The resultant force is going this way. That just means that the resistant force is actually slightly smaller than the driving force. Otherwise, the submarine is not going to move towards the right hand side. Instead, it will stop if both forces cancels out, or if it will move to the left if the resistant force is actually greater than the driving force, which is in reality is sort of not possible. It seems, of course, if there's no force to the right, there's no resistant force to the left. Alright, so in that case, when you use Newton's second law, F equal to ma, so the resultant force, ma, is equal to the force that goes to the right minus the force that goes to the left. Okay? Alright, so once we finish that, then we can divide m over, so that becomes 1 over m bracket F minus kV squared. And that's the reason why for the question they asked us to show why dv over dt is equal to that expression here. Since we know that a is equal to the derivative of velocity function in terms of time, and then we have proved. So that's a pretty simple and easy question here for part A. Alright, now for part B, we need to increase the speed from v1 to v2 and show the distance. So now we're looking for distance and speed, alright, the distance and speed function, the vx function or the xv function. Alright, so we're going to start from the one we had before. So question B, we're going to start from here. So A is equal to 1 over m F minus kV squared. We need to change this A into something that has velocity and displacement attached. All right, so that is dv over dx, which is equal to 1 over m F minus kV squared. All right, and then what you can do is divide both sides by the velocity. So that gives you F minus kV squared over mv. Alright. Okay, so once you have finished that, then we need to integrate it. Now please remember this, the denominator has an x here, okay? However, on this side is no x, so you can't really integrate both sides this way, so we need to do the reciprocal of both sides, okay? So dx over dv is mv over f minus kv squared. Okay, all right, so therefore x is equal to, you integrate, that's mv over f minus kv squared dv. All right, so that's pretty easy to integrate. Okay, so x is equal to m. All right, I'm just going to show you step by step working out. So we need to times by negative 2k to the top, f minus kv squared. That's because the derivative of the denominator is negative 2kv. So therefore, we need a negative 2k. All right, and then we divide it by negative 2k on our side. So that gives you x is equal to minus m over 2k, ln absolute value of f minus kv squared absolute value, plus c. Okay, plus c here. All right. Now we can sort of remove that absolute value just because of the force that going to the right must be greater than the resistant force. All right, it must be greater than 0. Otherwise, the summary is not moving to the right. So we can remove that absolute value and change this one to brackets. All right, so once we finish this, now we need to do the substitution to find out the change in distance from V1 to V2. All right, so the distance change is equal to, maybe I'll just put this one into the next page, just easier. All right, so the distance change from V1 to V2, we substitute V2 first, all right, and then minus V1. So that becomes negative m over 2k ln f minus kv1, no, V2 square plus c minus, then we substitute the V1, okay, plus c. So plus c should be here. Okay, all right, so now let's expand and rearrange. That should gives you, once you remove the brackets on this side, that becomes a plus, that will be a minus. So that becomes m over 2k ln f minus k v1 square minus, remember the c cancels out, okay, so I don't have to worry about the c, ln f minus k v2 square. All right, factorize the m over 2k outside, that becomes ln f minus kv1 square over f minus kv2 square. I hope that's the answer. Let's have a look at what the answer requires, if that's the right one. Yes, that is the correct answer here. All right, so m over 2k ln bracket f minus kv1 square minus over f minus kv2 square. So this is a really similar, very, very similar to question 3 that we did last lesson. All right, it's extremely easy. In this case, seems you already know the way to do the question, I hope. It's very important that you know the formula here, that you need to be able to use the Newton's second law, F equal to ma, to work out the answer. That is the resultant force. Here, this resultant force is equal to mass times by the acceleration. Okay, and the resultant force is the combination of these two forces together. All right, so that's question 5. All right, let's have a look at question 10. All right, let's hope question 10 will be slightly different to question 5. Okay, all right, so let's have a look at question 10. Question 10, a particle is moving along the x-axis. Its acceleration is given by this formula here. Now, if you look at this formula, that's ax function, acceleration displacement. It starts from rest when at x equal to 1. Rest means v equal to 0. Starts means t equal to 0. All right, so this is information I can have. Explain why the particles start moving in the positive x direction. All right, now, for this question, in order for us to answer that question here, what we need to do is we need to sort of talk about whether the acceleration is positive or not, and then we also need to say, what is the, I think if the acceleration is positive, And then if the particle is move it, initially the particle is at a positive direction, and if the acceleration is still positive, then it's going to start moving in the positive x direction. Okay, all right. So let's just write down everything we have. All right. So initially, when t equal to 0, velocity is equal to 0, x is equal to 1. Okay, that's initially. And then I will just need to do a very simple calculation by substituting 1 x equal to 1. What is the acceleration? So at x equals to 1, okay, at x equal to 1, the acceleration a is equal to 5 minus 2 over 1, which is equal to 3, and that is greater than 0, okay? So at x equal to 1, the acceleration is positive. The particle obviously moves in the positive direction. Alright, so therefore the particle starts moving in a positive direction. Okay, alright, now question B. Let v be the velocity of the particle. Show that v is equal to that expression here. So this is vx now. Okay, so now you think about the question. We have the ax function here. So let me just show a little flowchart here. We have the ax function. We need to change that into the vx function. The way to do that is we're using the formula v dv over dx to help us to do that. Okay, so once you know how to do the conversion, it's actually pretty easy. So let's just write down everything we have. Acceleration is 5 minus 2x over x to the power 3. So acceleration 5 minus 2x over x to the power 3. We need to find a way to actually change that into the velocity and the displacement function. So the first step to do is change the acceleration on the left hand side into v dv over dx. So now you have introducing the x and the velocity in the same time. Okay, all right. And once we have finished that, then what we need to do here is think about methods where I can integrate both sides. Now this time, you have to be very careful. Do not divide v over. Seems if you divide a v over, you have a v and an x in the same equation, which is not ideal. What you want to do is move the dx over to the right hand side. So you end up with v dv is equal to 5 minus 2x. Okay, just going to write properly. 5 minus 2x over x to the power 3 dx. Alright, so once you finish that, then you can integrate both sides. Alright, so that gives you, when you integrate both sides, it'll be integrate v dv is equal to integrate 5 minus 2x over x to the power 3 dx. Okay, alright, so that should be quite easy to integrate it. So that's half v squared. You can plus c here. That remember this is just c1. We'll also have another c2 on the other side. Now for this one here, in order for you to integrate it, just break that into two parts, like two fractions, right, before you integrate it. So imagine that is equal to, like, we integrate 5x to the power of minus 3 minus the 2x to the power of minus 2 dx. It's like this, all right? And then you integrate according to that. So that becomes x to the power of, all right, so you plus 1 to the power, so x to the power of minus 2, and then you do the reciprocal, that's negative 5 on 2. All right, and then in order for us to integrate the second term, you plus 1 again. So that becomes 1 plus 2 over 1 x to the power of minus 1 plus c2. Okay, so okay, move the c1 and c2 in and join them together. Just call that to like C. And then you can times everything by 2. And then you can write 2c if you want, but doesn't really matter because that is just equal to a constant c. Alright, so once we've finished that, let's go back to what we need to prove. We need to show the velocity is equal to the square root. Obviously, the square root comes from the square here. But then there is no c, so we need to calculate what is the value of c. So back to our initial condition here, when t equals to 0, v equals to 0, x equals to 1. Okay, so when x equals to 1, I'm just going to copy this one and move it to the next page. Right, so that's the formula we have here. When x equals to 1, the velocity is equal to 0. So if we do a substitution, c is equal to minus 1. Okay. Alright, so if we now substitute the c equal to minus 1 inside, that is minus 5 over x squared plus 4 over x minus 1. Okay, I guess the next step is making that into a big fraction, and the entire fractions here, making the same denominator. We should have x squared minus 5 plus 4x minus x squared. Okay, alright. No, that c is positive 1, yes. Okay, alright. Yeah, okay, so that gives you x squared plus 4x minus 5 over x squared for the v squared. So therefore, v is equal to the square root of x squared plus 4x minus 5 over x to the power 2. Now, we're supposed to have a plus minus for the velocity, but from the second part of the question, we already proved the velocity is positive, so therefore you don't need to actually write negative since x is greater than 0. So for x that's greater than or equals to 1, the velocity is also positive in this case. Okay, so that's question 10. So now if you look at these two questions, it becomes a sort of a standard question in extension 2. It's not that hard. The questions break down into 3 different parts. There's another part here, but and then you're just again changing from one equation to another equation using the method I showed you before. Alright, so let's have a look at question C. Describe the behavior of the velocity after the particle passes x equals to 5 on 2. So we need to know what happens when x is greater than 5 on 2. Okay, so how would you do this question here? Let's have a look from this. 5 on 2. When x passes 5 on 2. Okay. Question C. Question C. Alright, so velocity square root x squared plus 4x minus 5 over x squared. So when x is equal to 5 on 2, actually the question says what will happen if x is greater than 5 on 2. So the first step I need to do is let's just do a substitution. Okay, and substitute to see what happens when x is equal to 5 on 2. Okay, so if we substitute 5 on 2, alright, I'm just using my calculator to do the calculation here. Okay, the answer is equal to 1.34. So it's a pretty small number here. What does the question ask us to do? Okay, describe the behavior of a velocity after the particle passes x equal to 5 on 2. Alright. Okay, now let's have a look at acceleration. Okay, acceleration is equal to 5 minus 2x over x. 5 minus 2x over x to the power of 3. If we substitute x equal to 5 on 2 there, 5 over 2 here, then you should notice that acceleration becomes 0. Okay, so that what does that mean is the particles are actually initially accelerating. However, when x is equal to 5 on 2, the acceleration becomes 0. And then when x is greater than 5 on 2, I'm pretty sure the acceleration is become negative for x that's greater than 5 on 2, which means the particle is actually slowing down. All right, and if the particle keeps slowing down, the velocity is, obviously not, it's going to slow down as well, and the velocity is going to approach to a certain value. So in that case, what we need to do, I guess, is to find out or to sort of sketch a graph for this one here, and to see, when x is greater than 5 on 2, what does the velocity approaching to? Okay, so but obviously, in exam situation, it's pretty hard to actually sketch a graph like this. So another way you can do a question like that is you put a very large number into this expression there to see what is the velocity roughly equals to when x becomes a large number. All right. So in this case, let's have a look. We can do a limit question when x approaches to sort of infinitive, for the square root of x squared plus 4x minus 5 over x squared. Since we know the acceleration is less than 0 for x is greater than 5 on 2, so we kind of know that velocity is slowing down, but we just need to find out what is the velocity approaches to. Alright, so limit infinitive. Alright, so we divided both sides, the top and the bottom, by x squared, so we get 1 over 4 over x minus 5 over x squared. So in that case, that becomes square root of 1 plus 0 minus 0 after substituting the infinitive inside, which is equal to square root of 1, and velocity approaches to 1. Okay, from this limit questions here, we know that when x is approaching to, when x is it becomes infinitive large, greater than 5 on 2, the velocity starts to approaches to 1. Okay, slowing down and approaching to 1. Okay, so that's all for this question 10. I hope you understand the kind of ways this question is presented in this exercise. Again, the most important thing is be able to form the motion equations, so you can integrate or differentiate it. You can deal with that, play around with this function, to actually solve the problem according to what the question asks. All right, thanks for watching.